one of the most challenging sections in the entire physical science syllabus could be work, energy and power, especially when there's non-conservative forces. It's not too bad when you have everything in a closed system, but as soon as you get things like an applied force or a friction force, well then, it's not in this nice bubble of a closed or isolated system anymore.
Now friction is doing negative work, taking energy out of the system, whereas the applied force is going to be doing positive work, putting energy into the system. It's a bit like a reservoir. If it's a closed system, all the energy remains within. But friction is like a leak, and all the energy will slowly, gradually leak out. But an applied force is a bit more like a hosepipe, topping it up from the top.
These questions often have an object being dragged across a rough surface, or perhaps an object sliding down a slope, maybe a car driving up a hill. Basically, they love slopes, and so do we. That's why we're here by these hills for a bit of sandboarding.
So, you're in your exam, you've read the question, now what? Well, remember the 3D approach. It's the diagram, direction and data. So first up, the diagram. Now the question's most likely going to ask you to draw a free body diagram, but that's great because that's going to help you identify all the forces acting on the system.
You can check out our episode on forces and free body diagrams for a bit of help with that. And that's such an important step because work doesn't happen without a force. In fact, that's what work is, a force acting through a distance.
Sandboarding is a perfect scenario to look at work in a non-conservative system. I've seen a lot of questions set around the skier, and snow is not quite so accessible here in Africa. Here we are in our local hot and sunny setting.
Well, since this is not a closed system, we cannot use the principle of conservation of mechanical energy. Instead, we have to use work energy theorem, which states that the net work done on an object is equal to the change in kinetic energy.
So, there's a few more details that we're going to need to take care of, like deciding which direction is going to be positive, getting all the data together, and of course doing the calculation. But I think let's leave those details for another time, because it's time to get onto these boards.
Oh, yeah.
How's everybody?